Today is Thursday, January 22nd. This is Algebra 2 and Lesson 5-6. What? Somebody's cooking in the DLS room. I don't know. I gotta shut the door. Alright. Now Storm is gonna be like, what are we talking about? Alright, we should be on page 250. And today we're only gonna go over half the section. And then on Monday we have a 2-hour late start. 2-hour late start means class doesn't start till 1:25 p.m. So I know, Stormy, you probably won't be able to make it, but that's okay. And Jessica too. So I'll email this to your various teachers and we'll talk about it if we have to. So we're going to do half the section today and the other half probably on Tuesday. So this section is about radical expressions. So anything under the radical sign. Cube root, fourth root, fifth root, as long as it has a GH, AR, ER in Braille, and the weird V with a tail in print. And it's just different ways to simplify the radical expression using what you know about powers and roots. So basically, we're amping up last section. Amping it up a notch. Ugh. Okay. I'm looking, it's probably on, there's a paragraph that says simplifying radical expressions in giant capital letters. It's below the box, Jessica, where it says how do radicals expressions are used.
I found it.
Okay. Simplifying radical expressions. You can use, our favorite one, the commutative property and the distributive property of square root to find an equivalent expression for a product of radicals, such as radical 3 times radical 5. So we know the commutative property. What's the commutative property? Say. Yeah, you can commute things. You can move stuff around. We could say radical 5 times radical 3 is the same thing. Begin by squaring the product. Alright. So all they did is put that in parentheses squared. Open paren, radical 3, radical 5, close paren, squared, is the same thing as radical 3 times radical 5 times radical 3 times radical 5. Right? Because you need 2 of each thing, because it's squared. But then you can just reorder them due to the commutative property. So we could say that that thing is equal to radical 3 times radical 3 and radical 5 times radical 5. Well, radical 3 times radical 3 is the same thing as radical 9. Radical 5 times radical 5 is the same thing as radical 25. So that's the same thing as 3 times 5, which is 15. Because you can pull out one of them. They're squares. The square root of 9 is 3 and the square root of 25 is 5. So that's how we can do that. But since radical 3 times radical 5 is greater than 0, radical 3 in parentheses times radical 5 squared equals 15, which is the same thing as radical 3 radical 5 is the principal square root of 15. That's just a fancy math word of saying they're the same darn expression. So all I did was move some stuff around to get the same thing. 15 and then is the same thing as open paren radical 3 times radical 5 closed squared. And then of course that is radical 3 times radical 5 is the same thing as radical 15. Okay. That sounds confusing when I'm thinking about it, so let's look at what they're talking about. In the key concepts box. For any real numbers a and b, and any index n greater than 1. So remember, the index is what's the root, like the cube root. It's the thing between the GH and the AR in Braille, and it's the thing in the V in print. We can say, if n is even, so 2, 4, 6, 8, and a and b are both negative, then, or non-negative, excuse me, thank you, Miss Chris, then the nth root of ab is the same thing as the nth root of a times the nth root of b. So you can separate them out. All they're saying is if you have two things under a radical and they have an even root, you can separate them out kind of like the, distributive property. You can pull out the nth root of a times the nth root of b. And 2, if the root is odd, then the nth root of ab is also the same thing as the nth root of a times the nth root of b. So that's just saying if you have something like, let's say we had the square root of 25x squared, all under the radical. We could rewrite that as the square root of 25 times the square root of x squared. That's it. They're just saying, okay, we can separate the radicals.
Matter if they're even or odd.
Nope, they just had to separate them because they're being all math conscious. So that's just fancy math language. We could say the cube root of 8x cubed, cube root of 8 times the cube root of x cubed. So all they're saying is, okay, we can separate them out. And that's entirely up to you whether you want to or not. Alright, here we go. We have steps to follow. Follow these steps to simplify a square root. Alright, step 1. Factor the radical into any squares as possible. So as many squares as you can separate as possible. We did this a little bit last section. Because, the only way you can pull out something from a square root is to find its square. Separate them. Use the product property to illustrate the product squares. That's just saying apply them, separate them. And then simplify each radical when you're done separating them. Alright, let's look at example 1. Alright, square root of a product. Example 1. So here we go. Exactly what I said before. The square root of 16 p to the 8 q to the 7th. We have 3 different, I can't say terms because this is technically a monomial, right? There's no plus sign or minus sign anywhere. Inside. The square root makes it never mind. Sorry. Okay. We can separate these out into perfect squares. 16 is a perfect square. Q to the 8th is a perfect square, p to the 8th is a perfect square. Q to the 7th isn't, but we can rewrite it as the radical and say 4 squared, because that's the same thing as 16, times, open paren, p to the 4th squared, because p to the 4th squared does indeed make p to the 8th by the power of power rules. And we can separate q to the 7th into q to the 6th times q. So q to the 6th is a perfect square. It's q cubed to the squared. And then we just have a little old q hanging out. Okay. So this is nothing more than separating things into as many perfect squares as you could possibly find. So once you have it all pretty like that, you set them in their own separate radicals. So you would have equals radical 4 squared times radical q to the 4th squared times radical q to the 3rd squared plus that little radical q that we couldn't figure a place for. And the last thing you have to do is simplify each radical. So what's the square root of 4 squared? 4. What's the square root of p to the 4th squared? P to the 4th. And what's the square root of q cubed squared? Well, that's the absolute value of q cubed. Because remember, odd power, you have to put absolute values around it because it was an even root. And then we can't simplify radical q because we have no idea what q is. Q could be 125 and then we could do something with it, but it's not. So you have to leave q under the radical.
So it's all odd powers, not just a power of 1?
Yeah, all odd powers.
All odd.
All odd powers you put absolutes around if you started with an even root.
Oh, okay.
Except the 4, because we all know the absolute value. The reason they don't do it around numbers is because everybody knows the absolute value of -4 is always 4. Mm-hmm. We don't know with a variable, see? So they always put absolutes around the variables.
Okay, go ahead.
Okay. Is that scary to anybody? No? Well, that's good. You just have to break up the radical. That's all this is. It's kind of like when you first learn how to distribute. You have to break it up and simplify as you go. So, again, that radical q all by itself, there's nothing we could do further with it. It would be like if we had a radical 2. There's nothing you could do with a 2. It doesn't have a square root or anything. Okay, I don't hear any words, so I'm just going to keep on going. All right, we're at the top of the next page. We're going to learn how to divide them.
I do have a question.
Oh, good. What's up?
At the bottom it says, thus the absolute, it says, if that is true, Q must be non-negative.
Oh,
It's raised
sorry.
to an odd power, thus the absolute value is unnecessary.
Oh.
So,
Uh.
at the bottom.
Yeah, I'm reading. Oh. Right. Well, because remember, we can't have any negatives under the square root sign. Like, we can't say the square root of -2. We can't say the square root of -10. So the reason they're saying this can't happen is Q, if Q was negative, it would make the whole radical negative. So therefore it wouldn't work. So if you have absolute value signs, I'll accept it. Okay?
Okay.
It's okay.
Okay.
But yeah, that was actually just an extra critical thinking step. Like, oh, if the Q was negative, Q cubed would make that negative.
All right. So,
So.
we can put absolute value.
Yeah.
All right.
You might as well. Alright. Now, that was just with a bunch of multiply. What do you think happens when we divide? So I'm at the top of the next page, after the page break. Alright. Look at the radical that involves division to see if there is a quotient property for radicals. And of course, let me tell you right now, there is. That is similar to the product property. So it says, consider 49 over 9. The radical is, they're perfect squares. So if you have a big old square root with a fraction inside, so it's open root, open fraction, 49 over 9, closed fraction, closed root, is the same thing as open fraction, or open root, open fraction, and parens, 7 over 2, closed parens, squared, closed fraction, closed root. Yikes. A lot of braille, huh? So all I did was separate it. You can separate the 49 into 7 squared, and you can separate the 9 into 3 squared. And then, of course, remember, the square root of something squared is nothing more than that something. So the square root of 7 over 3 squared is just 7 over 3. So that indicates to us that we can separate. We can say, notice that also 7 over 3 is the same thing as radical 49 over radical 9. Because when you take the square root of 49, you get 7, and when you take the square root of 9, you get 3, which is the same. So this suggests the following property. So far we have learned that we can multiply and separate. Now we can divide and separate. So for any real number a and b, where b is not 0, why can't b be 0? Yeah, because it's in the denominator. We can't have fractions with denominator with 0 denominator. It doesn't make any sense. Can't divide nothing. Something divided by nothing. Like, it's hard to even think about what that means. 5 divided by nothing. Alright, so b can't be 0. And of course, n must be greater than 1 for your root. Because obviously, the first root of anything is always itself. So it just says the nth root of a over b is the same darn thing as the nth root of a over the nth root of b. Of course, if all roots are defined. So again, no 0. And then they give you an example. 27, the square root of 27 over the square root of 3 is the square root of 9, or 3. Because you can, remember, write it as a big one. So that would be the square root of 27 over 9. Or over 3, and when you divide 27 by 3, you get the square root of 9, and then the square root of 9, of course, is 3. Yikes! So again, we can separate by multiplying. We can also separate division radicals. It makes an intuitive sort of sense. Alright. I'm in the key concepts box, or concept summary box. A radical expression is in simplified form when the following the following conditions are met. So these things must happen in order for you to be done with your radical problem. Bullet point 1. The index n is as small as possible. So if you started with a fifth root and you got it down to a square root, but you couldn't go any further, that would be counted. The radical contains no factors other than 1 that are nth powers of an integer or polynomial. They're just saying, did you take out all the perfect roots in your radical? Like if you had radical 25, you couldn't just leave it radical 5 squared, because you could take the 5 out. So you have to take out as many roots as you can. The radical contains no fractions. Okay, don't leave it as a fraction with a radical. And then the radical, the radicals appear in a denominator. You can't have a radical number in the denominator. 0, none. So if you got an answer like 2 over radical 5, sorry, that would be considered unsimplified and I'd have to take a point off. And there's a reason for it, and you'll learn all about it, right, Josiah, when we get to I land. So just bear with me, accept it as reality. So no fractions, no radicals in the denominator. You took out all the roots, and the root is as small as possible. Those are the 4 little areas that you need to know about. So, here we go. This is important. We're going to use this a lot for the rest of the chapter. To eliminate radicals from a denominator or fractions from a radicand, you can use a process called rationalizing the denominator. Fancy word. It's just telling you to get rid of, that's how you get rid of fractions in the denominator. So to rationalize the denominator, multiply the numerator and denominator by a quantity so that the radicand has an exact root. So it says study the example below. Who remembers how we find a common denominator? What if we wanted to add 1/2 plus 1/3? How do we find a common denominator? This is similar. Yeah, they both fit into 6. And what you do, for instance, to make 1/2 into 6, you multiply it by 3 over 3, right? Mm-hmm. What's 3 over 3 just in general when you simplify? 1. This is the same process. In order to, so let's go back to my original example, 2 over radical 5. To get rid of the radical 5 in the denominator, you would multiply the numerator and denominator by radical 5 over radical 5. Just like you would with the common denominator. Because what's radical 5 times radical 5? Anybody know? What happens when you multiply 2 squares together? Right, you get what's out. You get the radicand. Because radical 5 times radical 5 is the same thing as radical 25. Well, the square root of 25 is 5. That's why they have you do it. So let's look at it in a concrete example, in example 2. It says simplify quotients. Alright, simplify each expression. And he says the square root of, open fraction, x to the 4th over y to the 5th, close root, and fraction. Okay, well, you got to start by separating this crazy stuff. So x to the 4th, luckily for us, is a perfect square, right? Y to the 5th isn't, though. So you would separate it into, the numerator is x squared squared, right? Because the square root of x to the 4th is x squared. And in the denominator, we can separate y to the 5th in such a way that we can make a perfect square out of it. So we can write y to the 4th times y in there, which is the square root of y to the 4th is y squared. So I'm about 3 lines down where it says equals, open radical, open paren, x squared, closed squared, over y squared, open radical of course, y squared squared times y. I feel like I'm saying squared squared a lot. But again, y squared squared times y, they just rewrote it. It's still darn y to the 5th. They just rewrote it so that we could take stuff out of the radical. And then next, they separated the 2 bottom radicals out. They left the x squared squared in the radical above, and in the denominator, they separated the 2. They separated out the perfect square from the y. So then they have radical y squared squared times radical y. Phew! Alright, and then when we simplify this crazy thing, finally, the square root of x squared squared is x squared over the square root of y squared squared, oi, is y squared. And of course we can't do anything with radical y. That one is just hanging out there in the denominator. But remember our rules up there. We cannot have radical y in the denominator. Just as a rule of thumb, we have to rationalize said denominator. And again, it's similar to finding a common denominator, because you have to multiply the entire fraction by radical y over radical y. Because again, it's the same thing as like 3 over 3. Radical y over radical y is nothing more than 1. It's just a fancy way of writing 1. So when you multiply, you're going to get x squared times, because it's just like multiplying fractions, numerator by numerator, denominator by denominator. X squared times radical y is just x squared radical y, because they are not like terms of any kind. And then y squared radical y times radical y is y squared times radical y times radical y. Radical y times radical y is just y. Your final answer is x squared radical y over y cubed. Okay, that's a lot to remember.
Why is it just
Well, write out radical y times radical y. What's radical y times radical y? Well, it's radical y squared, right? Because remember, from the very beginning of the section, you can combine if they have the same root, remember? So radical y times radical y is radical y squared. We can pull out the y because it's the square root of y squared.
what do you do that? Just put the y in there.
Yeah. You just simplify it. So if you ever see something like radical 2 times radical 2, that's 2. If you see radical 45 times radical 45, that's 45. If you say radical xyz times radical xyz, you just pull out the xyz. Because you're just doubling. You can combine radicals if they have the same root. And then you can pull out the same darn thing. Because that just means there's 2 of them, right? So, the numerator, x squared times radical y over the denominator of x cubed. So, hold on. I am going to actually stop here. That's it for today. I want you to get used to this concept first. I was going to go to the next one, but I'm going to wait. So, how about you do 4... there aren't many I can give you, but I'm going to give you as many as I can. 4, 5, and 4, 5, and 6 so far. I don't see many more I can give you right now. 4, 5, and 6, 15, 16. Oh, I haven't taught you how to do that yet. Never mind. 4, 5, and 6. It looks like it.
How about 8?
Good. And maybe 7. So I go 4 through 8. Start there. 4 through 8 would be good. I want you to get used to this before I bombard you with more radical stuff.
4 through 8.
Stop the recording. 4